between the graph and a closed has an area in many important in particular when the function is continuous or monotonic. A simple way to approximate this area is to draw in a rectangle by eye and compute its area. Or we might use the sum of the areas of two rectangular regions. Or perhaps we can do better by using 3, or 4, or more rectangles. We are going to show that the limit of such approximations is the area, and then introduce the definite integral as this limit. To illustrate the procedure, let's use a bounded positive continuous function f on a closed interval. To approximate the area under the curve, we proceed as follows. We introduce a partition called sigma, in which x0 is the point A, and the last point is B. The lengths of the subintervals in this partition are written delta x1, delta x2, and so on. The length of the longest subinterval will be called the norm of sigma. Now on each subinterval we pick a point and call it a star point. Let's take the subinterval as the base and the function value at the star point as the height to form a rectangle. Its area is an approximation to the area between the graph of f and the subinterval. Such a rectangle is formed on each subinterval. The sum of their areas approximates the area under the curve. Since this sum depends on the function f, on the partition sigma, and on the star points chosen, we use this notation for the approximating sum. If our discussion centers around a fixed function, we omit the f. For any fixed partition, there are many choices for the star points. And for any given norm, there are many partitions with that norm. Thus, there are many approximating sums for a given norm. But we shall see that they can all be made arbitrarily close to the area under the curve by choosing the norm small enough. In other words, the limit of the approximating sums as the norm goes to 0 is the area A. Let us return to a typical subinterval formed by a partition. Choosing the star point determines a rectangle. Because the function is continuous, there is a star point determining the smallest possible rectangle. It is an inner rectangle. There is another star point determining the largest possible rectangle, and it is an outer one. The increasing property of area tells us two things. The area of any star rectangular region is between the areas of the outer and inner rectangles. And the area under the curve is between the areas of the outer and inner rectangles. Now consider all subintervals in the partition. The union of the outer rectangles is an outer polygon, and the union of the inner rectangles is an inner polygon. Any approximating star sum lies between the area of the inner polygon and the area of the outer polygon, and the area under the curve lies between the areas of these inner and outer polygons. Suppose we are given a positive number p, and construct this rectangle so it has area p. Since f is continuous on a closed interval, if we make the norm of the partition sufficiently small, say less than r, then the difference in the heights of the outer rectangle and the inner rectangle on any subinterval is less than the height of our rectangle of area p. Thus, the difference between the outer and inner areas is less than p units. If the region under the graph is expanded so its area is increased by p units, and contracted so its area is decreased by p units, we have a kind of neighborhood of the function. The upper boundaries of the outer and inner polygons will lie in this neighborhood of f, so we can be sure that the outer and inner areas are within p units of a. Any approximating star sum is between the outer and inner areas. No matter how small the number p, a positive number r can be found such that for every partition with norm less than r, no matter how the star points are selected, every star sum is within p units of a. Now let us represent the area A as a point on a number scale, and look at the algebraic argument that A is the limit of approximating sums. If we are given a positive number P, we can choose an R such that whenever the norm of the partition is less than R, the difference between the outer area and the inner area is less than P. For different partitions with norm less than R, we may get different inner and outer areas, but they always differ by less than p units. The area A is always between them. So we can be sure that both the inner and outer areas are within p units of A for any partition of norm less than R. Any star sum is between the inner area and the outer area, so a star sum is within p units of A. No matter which star points are chosen, and no matter what partition of norm less than R is chosen, the star sum is within p units of A. If the norm is taken to be less than R, the whole set of star sums is in the p neighborhood of A. No matter how small a positive number p is given, a number R can be found that makes the set of star sums lie in the given p neighborhood of A. We say that the limit of the star sums as the norm goes to 0 is equal to A, and this limit is called the definite integral from A to B of f. The integral of a positive continuous function on a closed interval always exists and is equal to the area of the region between the graph of f and the interval. Now let's look at our argument again, assuming that f is non-negative on the interval, but not necessarily continuous. Suppose we can show that for any number p, a number r can be found such that if the norm of the partition is less than r, then the outer area and the inner area obtained from the partition differ by less than p units. Then it follows that the area A exists, and the inner and outer areas are less than p units away from A. Since any star sum is between the inner and outer areas, the set of all star sums is contained in the p neighborhood of A. And since for every p an r can be found, we see that the limit of the star sums as the norm goes to 0 exists and is equal to the area. This argument can be used to show that positive monotonic functions are integrable. Anytime the limit of the star sums exists, the function is said to be integrable. But if the function is not positive, the integral may not be the area of the region between the graph and the interval. Perhaps by examining a continuous function that is negative and one that is both positive and negative, you can discover the relationship of the integral to an area.